Hi. In the last video, I took what I believe to be the final clock circuit from the emulator into schematic form. And I believe I'm going to be able to use that all the way through the rest of this build. Today, I want to take a look at the register and its design and make sure that I've got that dialed in the way it needs to be as well. Recall that I've got a number of bad design decisions that I've made, a lot of which stem around some of the design decisions I made early on with the register. I need to go back and revisit that and correct those. That's the biggest flaw right now in the build, and I would say it is a fatal flaw. I have said that before. I'll continue to say that. Okay, let's get into it. Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. Okay, well, between recording the intro and now this segment, I managed to take a fall, actually. Was trying to get ready for our annual Christmas party and took a dive trying to straighten a rug out. Went down pretty hard. I don't think there's any permanent damage, but I did manage to mess up my right arm pretty good. And so I figured while I am not doing anything, I should probably solder and use my right arm for some very fine solder work because I got nothing better to do. So I'm using the technique that I tried a few videos back where I just put flux on the pads and add solder to the tip of the iron, and then not put solder on the pads and try to walk the component in, but rather just solder it in place. Okay, well, that worked. I'm going to clean this up and then I'm going to use this in the next segment. Okay, I want to take a minute and explore a little bit of the behavior of the 74HC193 up-down counters. Now I'm using the LS in Breadboard. I did double check this and they are the same, just formatted differently. But there was something I missed originally as I was going through this. This talks about the load signal, and specifically how the behavior is the output changes to agree with the data inputs independently of the count pulses. And I understood that objectively to begin with, but for whatever reason it didn't really sink in. And this is the focus of my test here today. I've got a 74LS 193. I've got the pin diagram right here on top, and then the LEDs that I just wired up. And what I want to do is I want to take the up and down signals and pull those high. I don't want them actually counting. A, B, C, and D inputs I'm going to tie or bring up here, and I'm going to set these low for the moment. Again, right-handed, and I'm struggling with this, so A, B, C, and D. Now my load line, I will take load, which is next to C. I'll bring it out here and I'm going to tie it high for the moment. And then my outputs, I'll need to come over here. So I'll just keep them in the same order I have them wired up here. A being the least significant bit, which is on the left, which is not traditional. But I'm going to stick with that just so that I can keep the order straight. I'm not dealing with counting, I'm dealing with loading. A, B, C, and D. Let's apply power. It's not powered up yet, but I do need to tie power and ground across. And then power. Nothing's getting hot. So if I switch this to be load, and I switch one of the inputs, I am expecting to see something come of that. Oh, you know what I didn't do? I didn't bring clear low. So let's do that. Clear is here. That should be brought low. There we go. Clear always overrides the load signal. Now I did take D and I moved it low. It immediately, without any kind of a clock pulse, turned that LED off. So if I bring it back high, it immediately turns on. And if I bring it back low, it immediately turns off. If I do the same thing with the next bit, and the next bit, and the next bit, that is doing what I had understood it to do, but it's also doing something that's very important in the build, and that is passing through the value that's being loaded, such that it stops actually responding to anything once this load signal goes high, and now I can make any kind of a change I want. All four of them are low now without changing the contents here. This is important because I can actually use this and potentially flatten a little bit the register architecture. So this signal could be brought low, this load signal could be brought low and left low for the entire clock cycle, allowing all of these inputs to change. They're being passed through to the output. Once things stabilize, hopefully there's enough time for the inputs to the outputs to update properly. And then on the rising edge of the clock, when this signal goes from low to high at the same time, everything can latch at exactly the same point in time, leaving me with a clean load cycle. And then on the falling edge of the clock, I can do any increment and decrement that I need, not loading, increment and decrement here. This is what led me to have problems with prior register. And that is, I figured those three signals should be mutually exclusive. And yes, while they should be mutually exclusive, they can't be driven in the same shape. The increment and decrement need to be driven in a different shape than the load does. Let me see if I can illustrate that and show you what I'm thinking now for the register. Okay, let's get into the current register design so that we can start talking about some changes that need to be made. The data path is pretty simple. It comes into 474HC183 up-down counters, and then the results get latched by a couple of 74HC574s. From there, there's really kind of an internal bus associated with the register, and those signals get distributed to 6 different methods to output that value. Now that's ALU-A, ALU-B, address bus 1, address bus 2, and a main and swap, which are 2 different entry points onto the main bus. Swap we've talked about a little bit. Ultimately, what that boils down to is when asserting the value of the register out onto the bus, the byte order is swapped. So the least significant byte becomes the most significant and vice versa. I've also got a couple of 74HC541 line drivers to drive the LEDs associated with the contents of that register. The control signals are split. There's a control signal to latch the register, the 74HC574. There are control signals to assert out onto each one of those buses through the respective line drivers. And then there's a couple of control signals that come into a demultiplexer, which then drive what's going to happen with the up-down counters, whether that is an increment, a decrement, or a load. And that shapes all 3 of those signals to be exactly the same. Again, I've got a couple of 74HC541 line drivers to control LED representation of what's going on. So what are we talking about doing here? Well, at minimum, I need to eliminate the 74HC139 demultiplexer. That actually is the single thing that is creating this flaw that has doomed this register. Those 3 signals need to come from the control module independently. They need to come on their own. And so that's going to increase pretty dramatically the number of control signals that I need. I'm willing to accept that. At that point, the register should work as it is. but I'm looking at one additional optimization that I think is potentially going to help me out tremendously. And that is to change the line drivers out onto each of the buses to 74HC 574 latches. Now, I've got a latch after a latch, so the original latches can go away, and then my line drivers simply become the independent 74HC 574 latches. That flattens out the register pretty significantly, and I believe that's a good optimization. Okay, let's see if we can emulate this design. Okay, and here we go. Currently have the register module emulating a program counter where it is incrementing on every clock cycle. I did test the load function and it's working properly, but with the increment, I need the increment to happen on the low going side so that everything properly latches on the high going side of the actual clock. And there's a problem here. Can you see it? Let me slow the clock down. Maybe you can see it. The increment is happening properly on the falling edge of the clock, but the LEDs are displaying that immediately, and I want it to display the actual value of the contents that are being available to be pushed out onto the bus. I'll slide this over and bring up my current design. So I also need a latch here so that I can latch and display the contents of the register congruent with what's about to be pushed out onto the bus. This value also needs to be latched at the same time as all the other latches that I'm now using. This was a good test. It revealed a problem before I ever had anything committed into Breadboard. So let me get that change made and we'll be right back with another test. Well, that's better. So as you can see, it's now showing the update in contents on the rising edge of the clock. I also have it now asserting out onto address bus 1, just like the program counter normally would, so that it could read the next instruction. And this is working well. I was not prepared for that change, but this is working well. Okay, so that said, now I need to get a little bit of a test harness built temporarily, just so that I can test each of the different functions rather than hard coding them into the emulator and then running that. So let me get a couple of radio buttons and checkboxes so that I can assert properly, and we'll see how that works out. Okay, and here we go. Now, right off the bat, I'm noticing something I don't like. I've got my oscillator running here, but ignore that for the moment. I'm in single step mode, and I'm interested in this actual clock. When I push the step button, the clock goes high, and I'm expecting that this is latching an increment. But the problem is I haven't done anything to trigger the increment yet, because it's when I release the step that the increment is to take place. So I'm pressing it, now I'm releasing it, and now I get the increment. I believe this to be a concern with not the register, but how I've got my clock module architected. I believe that when I'm in single step mode, I want the clock to be in a high state now, not a low state. That way, when I push the button and the clock goes low, in other words, assume that the blue is now turned off, the increment will take place, and then when I release, the clock goes high and the latch then happens. This is the beauty of being able to do this in an emulator. I should be able to identify issues like this and correct them before I am actually committed into hardware. So I've got a schematic. We did this in the last episode, and let me pull it out and we'll take a look at it together. And I believe I can identify the changes that need to be made. We can give it a test here in the emulator and see if that works the way we want it to. If I'm understanding my own schematic right, and that may be a stretch, there's only two changes that are required in order to make this right, make this work the way I want it to. The first change here is to change that to be a NOR gate instead of an OR gate. And that effectively will invert this clock signal. And that's what I need to get to. Now, this LED here is my breadboard representation, my PCB representation of that graphic oscillator that I've got in the emulator. And I believe I need to switch that so that it is an active high, or I'm sorry, an active low signal instead of an active high signal, meaning that this will sync current. That means I have to flip the direction of that LED as well, break that connection to ground, and instead connect it up here to VCC. It's also going to trigger a change of this from extra OR gates to extra NOR gates. And of course, all the pinning is going to change as well. But if I'm truly understanding this properly, those are the only changes I have to make in order to get this clock operating the way I want. I was thinking I might have to change this. I'm sorry, change the switch so that when the normally closed position, the circuit was pulled high. But I don't think I need to do that. I think I'm good with this the way it is. It keeps all of this circuitry exactly as it was, with the exception of that LED, except I'm inverting the ultimate output. I'm going to make these changes in the emulator first, and when I come back, we'll give it a test just to see what the results are. Now, before I go and make those changes, I'm going to do an interim commit here on my code so that I can roll back if I don't like what this is doing. Now, let me get that done and we'll come back to the emulator and test it again. Okay, that was a relatively quick change for me. Let's start by looking at the actual clock in comparison to the square wave. I'll slow this down a little bit. So when the square wave is high, the clock is on. When the square wave is low, the clock is off. So that's working like I expect it to. When I put it in single step mode, the clock is now stopping in the high position. When I step, the clock goes low and returns back high when I release. That's working properly as well. Now, if I go to increment, which was where I had the problem before, when I click to step, I believe it's incrementing in the background. And when I release it, it latches that. So I now have visibility to that on the first clock cycle after a reset. So let's turn that back up, reset again, clock, 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 clock. Okay. So overall, that's much better. I like that. Decrement should now work the same way, and I'll put it in single step mode so that when I release, it is actually doing the decrement. That's good. If I put something on the main bus, and recall that the ALU is the only thing that can assert onto the main bus, and I switch to load, when I step and release, this value then gets loaded onto the register. So that's good. And honestly, if I was to keep doing that, it would keep loading the same value irrelevant. But if I switch this now so that the register is asserting out onto ALUA, ALUB is being provided down here, ALUA, ALUB, add that together, I end up with this. But now if I go to increment and go to run mode, every time I increment the register, I'm getting a new value. Okay, I believe I was just dealing with an improper sequence of clicks the last time that loaded, because several things ended up getting loaded when they shouldn't have. So I believe this is good. I believe this to be a good change for sure, because I'm now able to track things much better. All the remaining circuits are just combinational. Relay Computer made that comment to me several videos ago, and it still resonates in my head quite a bit. Now, this was made from his second channel, but if you have a minute, go check out Relay Computer. He's got quite an impressive build going over there. Anyway, so what am I experiencing here? If you look at the behavior of the emulator, it's just combinational logic. There is nothing to add synchronization to when I turn on or off certain controls. Now, normally that would be in the control logic, but I don't have any of that built. I did briefly consider adding a latch to the register module to latch these control signals, but that's frankly the wrong place to put that. And since I don't have a control module yet, I'm actually going to punt this one. Now, I shouldn't be doing that, and I recognize that, but until I actually get something that will properly read the EEPROM binaries and load them into the emulator so that I can get a real faithful representation of how things are going to operate. I think I'm putting temporary fixes in just to turn around and take them back out again. So with that understanding, I believe the register module then is working properly. And so I've got two things to change now. The first is the clock module schematic, and I'll get that done in this video. The second is I've got to develop the register module in KiCad. And while I could do that and present that in this video, I actually want to wrap this one up and I will present it in the next video because I really do need to be able to figure out, based on that schematic, if I can bodge my current registers to work properly or if I actually have to switch this all out and do this differently. Anyway, let me get the clock module updated in KiCad. I'll come back and present those changes. Here's the updated schematic. Now, once again, I had three changes identified. One was to change the OR gate to a NOR gate. That was done here. One was to reset the oscillator LED so that it was an active low signal rather than an active high signal. That's been done here. And finally, the last thing was to change out the OR gates that I'm not using for the NOR gates that are unused. And that was done down here. Now, at the same time, I also renumbered all of the reference numbers. And so those have changed as well. And what I've done is not everybody has KiCad, so I have put a copy of the current schematic in that folder in PDF form. So you'll have the ability to download and look at this if you wish. I'll throw the link to the GitHub repository up on the screen, and it'll be available in the description as well. I'm quite pleased with where we managed to get to in this video. Unfortunately, I did have to take a detour back into the clock, but the reality is it was going to make the entire clock work better. Eventually, I would have realized that inversion problem in hardware once I got to the breadboards and things weren't behaving properly. But then I'd have to troubleshoot it at that point and try to figure it out and make changes. At least now I have a better chance of getting the hardware right the first time out. Soon I will be adding a couple more registers to the emulator to model what I've got built so far. And then once that's complete, I will be taking things back to hardware from the emulator. Now, I do have a few things that I do have to sort out before I can get to that point, one of which is the EEPROM replacement. I'm going to have to scrap what I've done so far and redo that just simply because it's too fragile at this point. I cannot rely on it to be accurate. Behind the scenes, I have had to reprogram them several times, and sometimes those have even made it onto video. I have no infrastructure for programming these, so I'm going to have to build that out as well. In the meantime, the next video will be translating the register module into KiCad schematics. See you soon.